Hello everyone. As I promised, I'm gonna go through a few rigid body dynamics problems for my class here at Embry-Riddle, but I hope this is also useful for those of you who will take a dynamics exam and you want to prepare for that, especially on the rigid bodies. This video could be useful for you. A few days ago, I published another video that was like 5 problems solved from particle dynamics. So this is the rigid body part. So the first problem says here you have this mechanism with 1 degree of freedom, which has a slider A that is going on this guide up and down. It is attached to this member A, B, C, or AC. And member AC is passing through the other slider, which is pinned down at point B. The velocity of A right now is 10 meters and it's constant going upward. You want to find the angular velocity of member AC as it spins and also the relative velocity of member AC through point B, because not only AC is spinning, it has to also slide through B, so it is gonna basically, in this case, move inside, right? Because this point goes up and the length of AC is constant, so C has to move this way, and of course this member has to rotate counterclockwise. You want to find those values. Also, you want to find the acceleration, angular acceleration of AC, and the relative acceleration or the rate of change of velocity of AC with respect to B. Okay, so there are 4 things that you need to find here. And if I want to write them, so velocity of A is 10 or like 10J if we go with traditional XY axes. And this is constant. And since V is moving on a straight line, that means the acceleration of point A is 0. And of course here you have units, right? So this is 10J in meters per second, and this is meters per second squared. Now, not every time an object moves with a constant speed, that means it doesn't have acceleration. If it moves on a circular arc or any arc, anything other than a straight line at a constant speed, it will have acceleration. It will have a normal acceleration. But in this case, it's moving on a straight line, so it doesn't. So the things you need to find are omega of member AC, as well as alpha of member AC, and V of point B relative. Relative to what? Of course, relative to member AC. And A of point B relative. Again, relative to member A, C, because B is a pinpoint, so relative to the ground, it has no velocity or acceleration, but relative to this moving member AC, if you attach a camera or any object that measures velocity or acceleration on member AC, you'll see that point B does have a relative motion. We are after those relative motion, velocity, and acceleration terms. Okay, and the important thing here is there are only 2 points that you can write the formulas for, and one of them is point B that you know something about relative to the ground. It has 0 velocity and acceleration, and also you have point A that you know its velocity and acceleration. So your points that you're going to use are A and B. The problem is A and B do not belong to the same rigid body AC. Why? Because B here is a point on the pin, and it's not on member AC. It's not moving. Okay, so B is a point that does not belong to AC. And so here we cannot write the simple formula and say, hey, V of B equals V of A plus omega of member AC cross R of B with respect to A. You cannot just simply say that. This formula is only valid if A and B belong to the same rigid body. And in this case, they are not. But if you watch my videos for sliding motion, and I recommend you go and look at them here. If you go to my playlist dynamics, let me just refer you to where you should be looking, and go to sliding motion for rigid bodies, and find the kinematics part, which is here, sliding contact in rigid bodies. If you go here to about 1 hour, 6 minutes, 27 seconds, you see the formula, right? VA is equal to VB plus omega R of A with respect to B plus an extra term VA relative. A relative to the member that has point B on it. Okay, so this is the formula. It has one extra term for velocity, and if you develop the acceleration part, you'll see that the acceleration part will have 5 terms in it. And one of them is AA relative, and the other one is a Coriolis term, which is 2 omega V relative. Let me show you that one as well. And these are those 2 formulas. Here we go. These are those 2 formulas we're going to use. So the first 3 terms are for rigid body, and these 2 extra terms are added because A can move with respect to the object that has BC, okay? So we're going to use those formulas. So what we need to add here in this formula is plus V of B relative. Again, relative to what? Relative to member AC. So this is the first formula that we have. Let's go ahead and fill it. So here, VB and VA are absolute velocities. They are both with respect to the ground. So VB is clearly, in this case, 0, okay? And VA is simply 10J, as the problem says. Omega AC, I don't know, right? It is either clockwise or counterclockwise. In this case, physically, we can see it's counterclockwise, but it doesn't matter. You can even assume it's clockwise. But whether it's clockwise or counter, it's either positive in the positive K direction or in the negative K direction. So Z-axis here is out of the board. So if you say counterclockwise, it's going to be positive K. If it's clockwise, negative K. And if you pick the wrong one, when you solve for that unknown magnitude omega AC at the end of the day, guess what? You're going to end up with a negative number if your initial assumption was wrong. If your initial assumption was right, then you end up with a positive number. So here, I assume that it is in the positive K direction. It has an unknown magnitude omega AC, which I don't know, but it is in the K direction. So that is that vector. R of B with respect to A here, it is going to connect what to what? It is B with respect to A, so it's going to go from A to B. So that is this vector here. This is R of B slash A with respect to A, which has a length of 1 meter, 30 degrees. So it is going to be basically cross, and let me get rid of that thing. I'm just going to write it up here. This is going to be -1 cosine 30 in the I direction, -1 sine 30 in the J direction. And finally, VB relative. This is the velocity of B relative to member AC. As I said here, this is assuming that you attach a camera here on this member AC and look at this point B. So the only motion that B can have, this fixed point can have with respect to this member that is sliding in this direction right now, is a velocity in that direction, along this member, okay, which is along the unit vector with angle 30 degrees. How fast it is, we don't know, but we know the direction of it. The direction of it is along the member. So here, for that, we can write it as VB relative, the magnitude, which we don't know, times the unit vector, which is cosine of 30 in the I direction. Sorry for my bad handwriting. I know this is not super beautiful, but I always have problem writing nicely on the monitor. So that's your unit vector. And now if you look at here, if you look at the 2 sides of this equation, you have 2 vectors that are equal, left and right, and that means the i's are equal and the j's are equal. Here, this k will be crossed with I and j, so you will get I and j. So everything is going to be I and j. There are 2 unknowns. One of them is this guy, omega AC. The other one is this VB relative, and that should give you 2 equations for the 2 unknowns. So if we continue here, as I said, the I coefficients are equal and the j's. On the left-hand side, there is no I, no j, so both of them are 0. On the right-hand side, there is a 10j. Then as we move on, we have k cross I. You know, k cross I is j, but there is a negative. So that's going to be negative omega AC cosine 30, right? Then we have k cross j, And k cross j is negative I, but there is another negative, so that becomes positive I. And then we have VB relative cosine for I. And we have VB relative sine for J. Guess what? 2 equations, 2 unknowns. I bet every one of you can do a simple elimination or use matrices. And if you solve for that, these are the numbers you are going to get. So your omega AC, if you solve for it, it is going to be 8.66 radians per second. And this is going to be basically 5 meters per second. Now, here, it is negative 5 meters per second. Okay, and this is positive. And what's the meaning of them? This positive means clearly the rotation is counterclockwise, which it is physically, if you remember. And what does that negative VB mean? Okay, let's look at that meaning of negative VB. So remember, we said that VB is in this positive cosine 30, sine 30. So we said VB relative is in this direction, but the number we end up was negative. So the actual VB relative, guess what? It is in this direction. It is opposite of that unit vector. So this is VB relative. Relative to what? Again, relative to this member. So it means, again, if you have that camera and you look at B right now and another time point, a few fraction of a second from now, B is going to get away from you. And that is right, because as we said, this member is going to slide into, so point C is going to go like this, as well as any other point on this member is going to go this way. So, but B is going to stay in the same place, because ultimately B is a fixed point. So B is going to stay at the same point. All other points are moving to the right. So with respect to them, B is getting away from them, which is this direction. Right? Those are V's of those points with respect to the ground. This is V of ground with respect to those points. It's negative of that. Okay, so we solved the first 2 parts of this problem. These are the first 2 things that we want. So now we got this VB relative as a vector. We figured that out. And this omega AC as a vector. These are those. Okay, now we go for what? We go for alpha AC and AB relative, and for that we have to write the formula that has 5 terms in it, if you remember, which is what? Here you say A of B. This is absolute acceleration of B. This is with respect to the ground. Is A of A absolute acceleration of A with respect to the ground plus 2 terms similar to rigid bodies, so it's going to be alpha AC cross R of basically B with respect to A, and then plus omega cross R, which for 2D problems you can simply write it as negative magnitude omega AC squared R of B with respect to A. Okay, so this term is actually this. This is like omega AC cross R of B with respect to A. But for 2D problems, this can simply be written like that. This is your normal acceleration, centripetal acceleration. So you can write it that way for 2D, and instead of 2 cross products, you can use a scalar times a vector, which is much easier to carry. And then plus 2 omega AC, this is the vector now, cross VB relative, and then plus AB relative. AB relative to what again? To member AC. So here we have 5 terms you need to figure out. And AB again here is 0 because this is absolute with respect to the ground. B is a pinpoint. AA is also 0 because A is moving 10J constant along a straight line. This alpha AC I don't know, but it has to be either positive K or negative K because this is a 2D problem. And there is no other way. Either the member will get bigger and bigger omegas in the counterclockwise direction, which means alpha is positive, or the omega of it starts to go down. That means omega is negative, but it's positive K or negative K. So since I don't know it, I just write it as alpha AC, its magnitude that I don't know, in the positive K direction. If it is negative, I will end up with a negative number. Okay, R of B with respect to A is what we had last time. That's the exact same thing. This magnitude of omega is that number that I have. That's just 8.66 squared, right? So that number I have from last time. And this was -1 cosine 30i, -1 sine 30j. Right? So omega AC is just that vector times the k direction, so it is just 8.66 in the k direction. VB relative is this number times that unit vector, so it is -5 times cosine 30i plus sine 30j. And AB relative is whatever its magnitude is, which we don't know, times its direction. And what is the direction of it? Well, AB relative is like the derivative of VB relative. And VB, if you remember, it was along this line, along the member. So if something is along the member, if something is only moving along this line, derivative of that should also be along the line, right? It's a rectilinear motion, that relative motion. So that should also be along the cosine 30i plus sine 30 what? J. Okay, now it could be again positive, or it could be what? It could be negative. Here we assume it is positive. If our assumption is wrong, guess what? We're going to end up with a negative number for that magnitude. So here we're just going to move this guy up. And if you look now, clearly, we have what? We have two equations again, because two vectors are equal on the left and right. They have I components and they have J components. And there are two unknowns, magnitude AB relative and magnitude alpha AC. Now, before I solve this, here you pay attention that you can only perform acceleration analysis if you know the velocities. Right? If I didn't know VB relative and omega AC, there would be no way I can find AB relative and alpha AC. So always velocity analysis should be done before what? Before acceleration analysis. That's a must. If you don't do it, you are not going to be able to what? You are not going to be able to solve the problem. And here again, if you look at the I's and the J's components, let me write them for you. So these are the two equations that you would get if you take the I's and the J's coefficients to be equal. And again, two equations and two unknowns. Everybody should be able to solve that. Alpha AC, you are going to end up with -86.6 radians per second squared. The negative clearly means it is clockwise. So your omega is going to go down over time, at least at this moment. And then A of B relative is going to be -75 meters per second squared. And again, that negative means it is in this direction. And V was in that direction too, so that V relative is going to increase in that downward direction. Okay, so here are the two other unknowns of the problem. And we found the two other ones up there, and this problem is what's over. So this is a kinetics of rigid bodies with sliding motion, which is the most complicated one, where for V you have to have a velocity analysis, you have to calculate 3 terms on the right. For acceleration, you have to go with 5 terms on the right. That is the first problem. Let's go to the second one. Okay, for the second problem here, we have the inverted pendulum on the cart. The length of the pendulum and the angle given, the masses are given. The system is released from rest if the friction between the cart and the ground is negligible, you want to find the acceleration of the block at that point, okay? So if this acceleration is a, you need to find it. And here, just for simplicity, we give a name to this pivot point. Let's call it point B, which is, we can also consider it to be like the center of mass of this block, although this block can be treated like, or the cart can be treated like a particle because it does not have any rotation, okay? It's the pendulum that you can treat it like a rigid body. And this is the centroid of the pendulum, which you might call it point G, assuming that it's midway and the bar is homogeneous. So the goal is basically to find acceleration of point B. So here we're gonna have two free body diagrams. One is for the block or the cart, and the other one is for the pendulum. And the forces on them is, it does not have any force on each side. It has a contact with the ground, which comes with the normal force. It says the friction is negligible, so we have the mass of the block, which we can show with capital M, times G. Okay, so let's call this 5 kilogram capital M, and the 2 kilogram of the pendulum small m. And also you have a pin here. Pin forces are a horizontal and a vertical one. So let's say the horizontal one is this way, right, to the right side, because as this object falls, actually it pushes the block to the right. So, and then also the weight is on this pin, so it is going to also push downward like that. And you might say, what if you don't have that mechanical insight, right? Couldn't you consider By upward? Yes, you can. But if you do and it's fine, you end up just with negative numbers. So it's totally fine if initially for Bx and By you do draw the directions in the wrong direction or in the opposite direction to reality. It's fine, you end up with negative numbers. And then here you're going to have the reaction to them, so there will be a Bx to the left and a By downward, and of course Mg. Okay, so here we neglected the friction as the problem says. So system is released from rest and the friction is basically negligible. So these are your FBDs. And each FBD has some equations, and we're going to go with the traditional XY. So for the free body diagram of the cart, if you look, some forces in the X direction, that is simply just Bx. That should be equal to mass times X double dot, where X here is X of point B. So the motion of this point, we're going to show it with X. That's the first degree of freedom, and the other degree of freedom that you have is the rotation to the angle, right? And here we can call this angle theta, right? Or you can call the angle from the vertical direction theta. It's totally fine. It could be either one, right? It has no problem. You can call either one. And most people will consider this as your theta deviated from that vertical direction. It is fine. In that case, your theta is going to be basically 35 degrees, this angle. So it's fine, whatever you want to consider. Since this angle is given with horizontal, I'm going to go and consider that angle as theta. Okay, so you have the choice, but you have 2 degrees of freedom. So that's that one, and then some force in the y direction that is equal to N minus mg minus By, and this is equal to my double dot, but y of the block is not changing, so this guy is simply 0. And if you don't mind, I would call these equations 1 and 2. It's always good to number your equations. It's a very good practice. The second one is coming from this second free body diagram. Now, another good practice you can do to organize your work is call this like FBD1, free body diagram 1, and this one to be called FBD2. So you can refer to them and don't draw those arrows. So these two equations are for FBD1, and clearly for the block there is no dimension, no rotation matters, and so there will be no rotation equation. And then for FBD2, the block, the pendulum does have dimensions, the rotation of it does matter, so you're going to end up with three equations for that, and some force in the x direction, that is negative bx, which is equal to mass times acceleration of point g in the x direction, some force in the y, which is by, right, if you can see, minus mg, equal m times y double dot g, and some torque about point G clockwise positive, y clockwise, because the direction of theta, okay, the actual direction of this angle theta, the way that it does work is it is going to go down. So that's the actual direction of motion, and so that's why I consider it positive. And if that's the case, then you see about the G, there are two forces that will create moment, and they are Bx and By, where for Bx, it's this vertical distance, and for By, it's this horizontal distance. And since this length here is 0.5, half of the member, and this angle is theta, so this angle here, that angle is 90 degrees minus theta. Then this vertical distance from here to here is simply 0.5 times cosine of 90 minus theta, which is sine theta. And this distance from here to here is 0.5 times cosine of theta. And Bx does create a clockwise moment, so Bx times 0.5 sine is positive. By does create a counterclockwise or negative, so it's negative By times 0.5 cosine. So we go down and we are going to write it. It is going to be, as I said, Bx times 0.5 sine of theta minus By times 0.5 cosine of theta is equal to I about point G times theta double dot, or the alpha. And I will call these equations 3, 4, and 5. I got 5 equations. Now I need to count the unknowns, see if I have enough of equations for them. I don't know Bx, I do not know By, I do not know N. I do not know x double dot. That's the unknown of the problem. I don't know theta double dot. And so far that's 5, right? Now if somehow I can figure out x double dot g and y double dot g in terms of x double dot and theta double dot, right, in terms of these two angular and linear acceleration terms, then I will have 5 equations and 5 unknowns, right? So if I can use kinematics constraint and the fact that there is a pin connecting the two members together, and connect and relate acceleration of g to b via rigid body kinematics equations, then yes, I will have 5 equations and 5 unknowns. So let's go ahead and use our kinematics now. Okay, so we're going to use our kinematics now. B and G do belong to the same rigid body, so we're going to relate their accelerations together. And we know that the system at the moment is released from rest. That means omega of this member BG at the moment is equal to what? Is equal to 0. If you remember in the previous problem, I said you cannot do angular acceleration calculations if you don't know your angular velocity. And here, the fact that it gives you the initial condition on velocity, that allows you to find the angular acceleration. So now we say what? We say acceleration of g, which is basically x double dot gi plus y double dot gj, these two unknowns, is equal to acceleration of b plus alpha of member bg cross r of g with respect to b minus omega of member bg squared magnitude r of g with respect to b. Now at the moment, the member is starting from rest, so that is 0. A of b is clearly what? It has x double dot and y double dot of 0, so this simply is x double dot in the I direction. Alpha of member BG has to be either clockwise or counterclockwise. We don't know what it is, although we can guess because the system is starting from 0 velocity and it's going to fall down, so it has to be counterclockwise, so it has to be positive k. But even if we don't know and we guess negative k, guess what? We're going to end up with a negative number. And r of g with respect to b is connecting connecting b to g. Okay, so it is basically, if I want to do a little bit of cleaning, it is basically this vector here, this vector. And it has a length of 0.5. And if you look, this angle is theta, so it's going to be negative cosine theta in the I, positive sine theta in the j. And theta is 55, so we can directly write 55. Right? So let's go ahead and do it. Okay, we go to the third problem now. The third problem is a pendulum released at angle 0, position 1, and it goes to angle 2, and which is 60 degrees, position 2. One end of it is attached with a spring to another pinpoint. The mass of the pendulum is given, the k for the spring and the unstretched length for the spring is given. The system is starting from rest. You want to find omega of the pendulum in position 2. So let's see how we do it, and we have to use work energy for this problem. So the unknown to be found is omega 2, right? Because omega 1 is 0. So if you draw the free body diagram of the pendulum at arbitrary angle theta here, there are 3 forces acting on it. There is this mg, and there is ax and ay. And of course, we're going to use the traditional xy coordinate here. And I would call this center point G. Now we write the work energy equation, which is W12 of all of these forces is equal to K2 minus K1. Now here, AX and AY will not do any work because they are applied to a fixed point. Only MG does a work, and this should be equal to K2 minus K1, okay? And this object is spinning about a fixed point, so it is doing a pure rotation. So we can say the only kinetic energy it has is kinetic energy due to rotation. Now kinetic energy 1 is clearly 0 because you start from rest. Kinetic energy 2 is 1/2 I about the pinpoint A times omega 2 squared. Okay, since it's a pure rotation about the point, I can write a pure rotational kinetic energy. And this is clearly negative mg delta y of the centroid. Now, in this case, I about A is ml squared over 3. And delta y of g is basically this distance, right? As you go from theta of 0 to theta of 60, which is clearly, since the whole length is 1, each one of them is 1/2. And when that angle is 60 degrees, that side is going to be what? 1/2 times sine of 60, and it's downward, so it's negative 1/2 sine of 60. And everything in this problem is known except for omega 2. And guess what? If you solve for omega 2, your answer is going to be 3.33 radians per second. Done. Okay? So that is the third problem, which is done with work energy. Of course, you can solve it also with Newton method, but here we are solving it for work energy, so you see a different solution. So here I solved 3 problems for you, and as a bonus, I'm going to solve a 4th problem, which is a very good problem. This involves, again, 2 blocks, 2 objects that are connected, and we're going to use Newton method for it. It's a kinetics problem, so it involves also kinematics in it. And so it's similar to this inverted pendulum on the card problem, but even a little bit more complicated than that. That's very interesting. And before we go to this final problem, let me just emphasize that these 4 problems, their pictures, the problem description, they are again coming from the book Engineering Mechanics Dynamics by Bedford and Fowler. Okay, so these pictures do not belong to me. They belong to the authors of this textbook, which is a relatively good textbook. I use it for my classes. And the goal here is just to go through these solutions. So this is the last problem that I said that is a good bonus problem. Here you have a homogeneous disk with mass 4m and a bar with mass m, slender bar. They are attached with a pin. The system is released from rest if the disk rolls without slipping, and the friction between the end of the bar and the horizontal surface, this point here, is negligible. You want to find the alpha of the disk. Show that it is 6g/95r counterclockwise if the system is released from. So here we need to draw 2 free body diagrams, right? One is, because we're going to use a Newton method, although even if we didn't work energy, we still needed the free body diagrams. So here is the first one, and here is the second one, and I would like to give these points some name. So I call this centroid G1, I call this centroid G2, I call this pinpoint point B, and I call this contact point here point A, the important points, the points that we know something about them. Either they are centroid or they have a limitation, a constraint, like this point A is basically being slipped on the being moved on the ground, or point B, which is basically the common point, the pinpoint. Okay, let's look at the forces. So the obvious forces are, of course, on this one you have mg. On this one, you have 4 times m times g, right? Because the mass is 4m. Then you have a pin. So there are 2 pin reactions. And there is a normal force here, and there is a normal force there. So for instance, I can call this N1, I can call this N2. So there are pin reactions, 2 here, the reaction to them here, and the friction. Now, the pin reactions are not that critical if you draw them in the positive or negative x direction for one of them, and the reaction of that, of course, for the other one. The only thing that you cannot make a mistake here about, right, that is the friction. The friction here, which causes the object to roll, because here there is no friction. Okay, here it says what? The friction is negligible. But in here there is friction, and if you make this mistake about the direction of that static friction, that is not going to be good. That is because the friction only has one direction. It opposes the potential motion. It never helps with the potential motion. So if you do it the other way, you have ruined the solution. So we have to have a little bit understanding of how the system works. Now this block, this disk, does not move by itself. If you just leave it there from rest, nothing is going to happen. Okay, because the centroid of it, as it moves, only stays on this horizontal level, so it never loses potential energy due to its motion, so it's not going to go any further to the left or right. But this one acts like a pendulum here, and if you let it go, basically this wants to drop like this, because this point is a contact point with the ground, and the centroid If it rotates, it would like to come down. When that happens, this contact point, also this point B, is going to come down as well. Okay, so this object is going to rotate clockwise like that, and B wants to come down. When B wants to come down, it is going to push the pivot point on the disk to go down with it like this. Okay, and reaction of that is going to be like that. So this is the By on both of these objects. Now By is not as critical as Bx is. So what about Bx? What's going to happen? This point also has no what, has no friction to keep it in place. So how does point A move in this situation? And the answer is, if you look at this block, and since this point is going to go down like that, and this point has to move horizontally, the only possible motion for A is to move to the left. It cannot move to the right, because if it does, and this point goes down, that means the beam has to shrink, right? The length of this beam or slender bar cannot change. The only way that it cannot change is as this guy comes down, this one goes a little bit to the right like that. If this one goes this way and this one comes down, then you're going to have a shorter member, which is not possible. So the only motion here for the contact point A is to horizontally go to the left. Okay, that's right. And when this point moves to the left, the centroid, if you say this is the center point, okay, since this is the center point of the points A and B, the velocity of it is going to be the average of these two. So this is like V of A, this is kind of like V of B. So G1 is going to be the average of the two, so it's going to have some motion to the left, some motion downward, so G1 is probably going to go like this. And so the whole object, as you can see, has some left motion in general, right? The centroid of the object has the tendency to take the object a little bit to the left. And if that's the case, this object in general wants to come down and to the left, it is going to pull this disk with itself to the left. So the force that it is going to apply to the disk is like this. This is your Bx. Of course, the reaction of that is going to be like that. And if Bx wants to pull the object this way, the friction has to stop it. The friction should not allow the object to be moved to the left. And the only answer for that is that static friction is this way, to the right, to stop the object from sliding to the left. And for that reason, the direction of friction in this case has to be to the right. If you do it to the left, guess what? You are going to end up with the wrong answer. This is extremely critical, this analysis that I did for you here, so you can get the proper answer. Okay, now that we got it, let's go ahead and Let's go ahead and write the equations. And here I call this FBD1 again, and I call this FBD2. And we're going to use traditional XY frames. And we're going to write our equations. So here, FBD1, we're going to have three equations. Some force in the x direction is clearly only Bx. This is equal to mass of that member, m, times acceleration of G1 in the x direction, x double dot of G1. Then some force in the y direction, that is equal to N1 plus By minus Mg. That should be equal to M times Y double dot of G1. And then some moment or torque about point G1. And in this case, the object is going to go clockwise, so you can do moment clockwise, okay? Because that's how this member is going to spin. So we go clockwise positive. Although, if you want, you can do counterclockwise positive, and the reason is here your z-axis positive is outward, so counterclockwise is positive rotation. But if that's the case and you want to make the rotation counterclockwise positive, which is fine. You have to know that your object is going to go like that, because initially you're starting from rest, so your alpha of this member is going to be like that. Okay, it's going to be, if I call it alpha 1, this alpha 1 is clearly going to be clockwise. So when you write it equal to I about G1 times alpha 1, you have to know that alpha 1 is negative. So to avoid that, here I start with clockwise positive direction. And with respect to that, clearly you see that you have N1 with this distance and By with that distance, and then Bx is with this vertical one. And so at the moment, the first thing is, what are these distances? So if you look, this distance from here to here is r. That distance is 2r. So if you want each one of these vertical distances, clearly they are r over 2 and r over 2. And if you want each one of these, they are r and r. So this is r, this is r, this is r over 2, and this is r over 2. So sum of the moment clockwise positive for G1, N1 does create a clockwise moment, so that's positive. By is negative, and Bx is also positive. So it's going to be positive N1 times R minus By times R. Okay, so let's go ahead and write it. N1 times R minus By times R, and positive Bx times R over 2. This equals I about G1 times alpha 1. Similarly, we go to free body diagram number 2, and we write the equation. So some x force in this case. We go and take a look. We have positive F and then what? Minus Bx. Positive F and minus Bx. So let's write it. This equals 4 times m times x double dot of G2. Some force Y equals N2 minus 4mg minus By. This equals again 4m times y double dot of G2, and summation of the moments about G2. Now let's look at G2, see how this member is spinning. So in this case, the object wants to be dragged to the left, the friction is to the right, so the only solution for that is your alpha 2 is counterclockwise. And so we go counterclockwise positive about G2. And if you look at G2, the only forces that create a moment for G2 are Bx and F. Or sorry, By and F in this case. Because N2, 4mg, and Bx pass through G2 at this moment. So By is clearly positive and F is also clearly positive. Both of them have a distance of r. So it's going to be F times r plus By times r. And this is equal to I about G2 times alpha 2. So let's number the equations. Equations 1, 2, 3, 4, 5, and 6. We got 6 equations. Let's see how many knowns and unknowns we have here. So Bx is clearly unknown, By is clearly unknown, N1 and N2 are clearly unknown, static friction is clearly unknown. Y of G1, x dot and y double dot of G1 can be related to alpha 1, so we don't consider them unknown. Alpha 1 is unknown, alpha 2 is unknown, and x double dot of G2 and y double dot of G2 can also be related to alpha 2. So if you look at them clearly, you have two unknown alphas, 2bx, by, n1, n2, and static friction. That's 7. You got 7 unknowns and 6 equations, even if you know the double dots. Okay, right now we don't, so we have to see how much we can get out of kinematics, because we clearly have 7 unknowns here, and we need to basically have enough equations. How much is I about G1 and G2? Well, G1 is a slender bar, mass is m, length is, we have to find it because one side of it is 2r, one side of it is r, but remember that it is basically length squared. So this one is mass times length of AB squared over 12. That's the center. And clearly this length of AB squared is r squared plus 2r squared. So it's going to be basically 5r squared. And I about G2, this one is a disk. The radius is r, the mass is 4m. And if you remember from statics, the inertia for a disk with mass m and radius r is 1/2 mr squared. So this one is going to be 1/2 4m times r squared. So as you see, we have 7 unknowns, 6 equations, and we still have to find out these x double dot and y double dots for the centroids. So now let's go to kinematics and see what equations we can get from kinematics. So in kinematics, we know that we can find acceleration of point B from G1. Also, we can find it through G2, right? Because it's a pinpoint. That should give us some equations. The other constraint we have here, so one constraint here is these disks are attached by a pin. The other constraint you have is this disk is rolling without slipping. That should give us some relation for acceleration of point G2. And also this A that is being dragged on the ground and it only moves horizontally, that's another constraint. So we have 3 constraints. We have to write them mathematically. The disk rolling without slipping, that makes life a lot easier on us, because if it's rolling without slipping, clearly the only motion that G2 has is due to rotation. By the way, G2 does not go up and down, so y double dot of G2 is clearly 0. So if we go and look at this equation here, this one is clearly 0, okay? That one is out of the picture. Now, x double dot of G2, as you know, when a disk rolls without the slipping, radius is r, acceleration is alpha. This is clearly r times alpha. Okay, but pay attention that your alpha number 2 is counterclockwise. That makes point G2 to be accelerated to the left. So if we want to write something for acceleration of G2, since it's opposite of the x, it should be negative r times alpha 2, okay? Be careful about these signs. If you make a mistake about these signs, that can easily change your final answer. So this is negative of what? R times alpha 2. Okay, so 2 of these double dots are out of the picture. Now that we know the acceleration of point what? Point G2 perfectly, from that we can find B, and then from B we should be able to find what? G1, or relate these two together to say that acceleration of B, whether you find it through the bar or through the disk, is the same. That should give you relations between alpha 1 and alpha 2. And then we also will visit point A. So first, let's go to the fact that B belongs to both of the rigid bodies, see what that gives us. So we say that acceleration of B, whatever it is, I can find it through point G1 plus alpha of member 1 cross r of B with respect to G1, and then minus omega of member 1 squared r of B with respect to G1. And I can write the similar thing for the second member because I can find it through the second member, through the disk. So it is going to be like this. Now note that the system here is released from rest. So both of these omega terms are 0. That is really good. You have some simplification. A of G1 here can be written in terms of the two unknowns that we have for it in equations 1 and 2. So this one can be written as x double dot of G1 in the I direction plus y double dot of G1 in the j direction. For G2, it was similarly just negative R alpha 2 in the I direction. That was known. Alpha of member 1, remember, is clockwise, so it's simply negative alpha 1 times k. For member 2, it is counterclockwise, so it's positive alpha 2 times k. And then we have R of B with respect to G1 and R of B with respect to G2. Well, if you go and look at the picture, B with respect to G1 is this diagonal vector going from G1 to B. So if I use a something like that, this is the vector I need to find. And for the other one is like this. So B with respect to G2 is simply negative R in the I direction. For this one, if you remember, the horizontal portion is R, the vertical portion is R over 2. Okay, so if we go back here, the first one is going to be Ri plus R over 2 in the j direction. And the second one is simply negative R in the I direction. So this is negative R in the I direction. This is positive R in the I and positive R over 2 in the j. And here clearly you have two vectors equal, this vector and this vector. That means the i's are equal and the j coefficients are equal. And if you expand it, let's see what equation that will give us. Okay, one of them will be like x double dot of G1 in the I direction. And then you have here a k cross j, which is negative I, but there is another negative, so that becomes a positive R over 2 alpha 1. This is on this side. And for j of it, you have y double dot of G1. And you have again k cross I, which is j, but there is a negative. And on the other side, we have negative R alpha 2. And then we have k cross I, which is j. But there is again a what? There is a negative involved, so that is going to be negative R alpha 2. Okay? And clearly from here, you can get both of those double dots. So your double dots, x double dot of G1 is clearly negative R alpha 2, negative R over 2 alpha 1. And then y double dot of G1 is negative R alpha 2, positive R alpha 1. Okay, and I would call this 7 and 8, which are going to be implemented in 1 and 2. So now, if I implement this 7 and 8 into 1 and 2, I really will have 6 equations, and as I said, 7 unknowns. So I need one extra equation, and that comes from this last point A, that is only capable of moving on the floor horizontally. For that, I go from G1 to A and I try to find acceleration of A, okay? Or I can go from B to A if you want, because B is easy to find. B can easily be found through G2, right? Because G2, the acceleration of that is perfectly known. And since B belongs to that member, B can perfectly be known, and then I can go from B to A, find the acceleration of that, and then make it to be only horizontal, or only in the I direction. That is a better way to not include this point G1 in the middle, and directly go from G2 to A. And if you go back and look here, actually, this guy here, this is your acceleration of B, remember? And how much is it? Remember, this is K cross I, which is J negative. So it was, if you look at that, it was basically negative R alpha to I and negative R alpha to J. That is acceleration of B. So now I can go from B to A and say A of A is equal to whatever it is. It has some magnitude and it's only in the I direction plus 0 in the J direction. This is equal to A of B plus alpha of member 1 cross R of A with respect to B, and then minus omega of member 1 squared, again R of A with respect to B. And again, omega is 0 at the moment for both members. And this one, I just have it. It was negative R alpha to I, negative R alpha to J. This alpha 1 here is just negative alpha 1K. And R of A with respect to B, you go from B to A. So that is this vector here, like this, which is negative 2Ri, negative Rj. Now, if you look, I have two vectors, and I don't want to introduce this extra unknown A of A into the problem. I only look at the J components of both sides. Because for J on the left side, it's simply 0. So I only look at the J's, 0 on the left, and on the right, whatever J I have, that's a negative R alpha 2. And also I have a K cross I, which is J, and both of these negatives would cancel. So you're going to get plus 2R alpha 1. This is 0. Guess what? This gives us a very nice thing, and that gives us that alpha 1 is actually alpha 2 over 2. You see? So this guy can be called equation 9. And now if you plug 9 into 1 to 3, where alpha 1 would appear, why alpha 1 would appear? Because once you plug in 6 and 7, 7 and 8 into 1, alpha 1 will appear into x double dot g and y double dot g. So all equations 1 to 3, they will have alpha 1 in them. Therefore, this new result that we got, this 9, should be plugged in all 1 to 3 new results, and that will give us alpha 1 out of the picture. Okay, so here, let's use some new notations. This equation, if you don't mind, 7 in 1, I would call it equation 10. And 8 in 2, I call it 11. And now 9 is going to go into both of them. And also, it is going to go into the equation number 3. So now your equations are going to be 3, 10, 11, 4, 5, and 6. And all equations are linear, so if you write it in terms of a matrix and solve for all 6 unknowns, one of your unknowns is alpha 2, which is the same alpha here. And guess what? If you solve using, let's say, MATLAB symbolic, you can easily show that the solution is actually 60 over 95R. Okay, these are your 4 problems. Hopefully they help you prepare for your upcoming exam or in the future. Thank you so much for your attention. I'll see you in the next video.